So welcome back to our algebraic graph theory seminar. Today, Yuval Filmus is going to tell us about the orthogonal basis of eigenvectors for the Johnson and Kneser graphs. Okay. So yes, when you want to start your talk, you can unmute yourself and then we'll.
Yeah, sorry about this. So now you can hear me, everybody, and you can also see my screen in a moment. Great. Okay, so this is based on joint work with Nathan Lindzey, who is now at the Technion. So I'll start with a quick introduction. I'm sure we all know what the Johnson and Kneser graphs are, but we'll go over the definitions again anyway. And then we're going to discuss what the eigenspaces of these graphs look like, culminating in an explicit description of an orthogonal set of eigenvectors for these graphs. Okay. Oops, sorry. So we start with an introduction. Okay, so we let k and n be two parameters, two integer parameters, where we'll assume for convenience that k is at most n over 2. So the Johnson and Kneser graphs, the vertex set of these graphs is the so-called slice. So the slice, I don't know if this name is very popular in your circles, but it's become popular in my circles. So this is just the set of all subsets of the numbers 1 up to n, which have size exactly k. Oops. Which have size exactly k. Okay. So the Johnson graph the vertex set is, well, the slice. And we connect two sets, S and T, if their intersection has size exactly k minus 1. Okay, and another graph has the same vertex sets. And we connect two sets if they're disjoint. Okay, so as an example, an intersecting family of sets is the same as an independent set in the Kneser graph. And that's maybe why some people in the audience know these graphs from. Okay, now it's well known that these two graphs have the same eigenspaces, and actually, if you take any graph in the slice where the weight of an edge, so it could even be weighted, when the weight of an edge depends only on the size of the intersection, then it will have the same eigenspaces. Yeah, so both graphs have the same eigenspaces. This follows from the classical theory of association schemes. And we will denote them by V0 up to Vk. Okay. And our goal in this talk would be to try to understand what these eigenspaces look like. Okay, so we'll start by describing them in one way, and then we'll find an explicit basis, which won't be orthogonal, and finally, we'll describe an orthogonal basis. Okay, so some of this might be familiar to most of you, but just bear with me. Hopefully, it will be something in this talk for everybody. Okay, so questions before I go on? Great. Okay, so this was part 1, and part 2. This is going to be stuff which I'm going to attribute to Dunkl, but maybe this is false. So Chris, if you know better, then please let me know. So this will be a way of describing these eigenspaces in a particular way. Okay, so the slice, and choose k, which I remind you is just a set of all k subsets of n, is the same as this permutation module mn minus k k. Okay, this is something that arises in the representation theory of the symmetric group. So this is the linear span of all partitions of n into sets of sizes n minus k and k. Okay. Now, from the classical representation theory of the symmetric group, worked out by some people like more over a century ago, we know that this thing decomposes as follows. And decomposes it as a sum of the so-called Specht modules. Okay, which, well, as we go on, then we'll actually sort of describe them. Okay. And as it turns out, these modules are the same as these eigenspaces that we mentioned above. Okay, so finding out a description of these eigenspaces is the same as finding out a description of these Specht modules. But there's a slight difference between what we're doing now and what people usually do in representation theory. So for people doing representation theory, this thing is a module. It's something abstract. It has no connection to the slice. But we want to understand how this Specht module, this copy of the Specht module, how it looks as part of the slice. Yeah, this is what we're trying to do. Maybe this will be more accurate. Yeah, so if you read books about representation theory, they don't bother with these things because they're very abstract, but this will be more hands-on. Okay, so another way of thinking of the slice, just a way to code sets, is as the set of all Boolean vectors. Okay, x1 up to xn in 0, 1 to the n, with exactly k many ones. Okay, and now the way we're going to describe functions on the slice is in terms of this type of input. Okay, this makes sense in some perspectives. For example, if you're doing Boolean function analysis, then this is very natural. Okay, and in particular, as we'll see now, we can write any function here. So you can think of this as a function from the slice to the reals, or maybe some of you prefer complex numbers. So just whenever I write R, just mentally replace it by C. So we can write any of these functions as a bona fide function on these coordinates, where the promise is that these coordinates are always either 0 or 1 individually, and exactly k of them are 1. Okay, so let's see how to write every single function on the slice in this way. It's going to be very, very stupid. So we have a function f, which is a function from the slice to the real numbers. And it's going to accept these inputs, and we can write it in the following way. So we go over the entire slice. Okay, and now we take the value of the function. So now we're thinking of the input as a set. And we're taking the following product of xi for all the I in S. So the point is that this product here is a delta function. The only way in which this thing is equal to 1 is if the input is exactly the set S. Okay, so this is why this identity is true. Okay, there's really nothing deep going on here. I'm just writing it in this somewhat strange way. Okay, and now let's see why we're doing it. So we're defining the following operator, the formal derivative. So delta of f, this is going to be just the sum of all the partial derivatives of f. Okay, so if you want, you can think of it as the usual derivative, and if you don't, then this is just the formal derivative. And actually, later on, we'll see another way of expressing that this is a formal derivative. Okay, so why are we doing this, or rather, why was Dunkl doing this? So if you take a function represented in this way and you apply this operator, then okay, so this function was a multilinear polynomial, which is homogeneous of degree k. And if you apply this operator, then the degree reduces to k minus 1. So you can think of this operator delta as taking a function of the slice nk and outputting a function on the slice nk minus 1. Okay? So just if you apply this operator, then now all the monomials will have degree k minus 1 rather than k. Now this thing, as we know, this decomposes as a sum of Specht modules in this way. And this thing decomposes as a sum of Specht modules in a very similar way. Okay, so you can notice that one of these Specht modules is missing. Yeah, these two expressions are almost the same, but one of the modules is missing. Now, it turns out that this operator delta has full rank, and you can see this using something we'll see later on. And this implies that if you take the kernel of delta, then you got exactly this Specht module, which is missing from here. Okay, so it turns out that this Specht module Sn minus kk is the kernel of delta. Okay, so what does this mean? So Vk is the space of all multilinear polynomials which are homogeneous of degree k and in the kernel of delta. Okay, so this is what I think of as an explicit description of this kth eigenspace of the Johnson and Kneser graphs. Okay, so you take any polynomial you want, which is multilinear and homogeneous of degree k in these variables x1 to xn, and it needs to satisfy this additional condition that it's in the kernel of delta. So if you apply this delta operator, you have to get 0. And we'll see later on some examples, or actually all examples of polynomials of this sort. Now here is a piece of notation. So we call polynomials lying in the kernel of delta harmonic. Okay, and this is not my own invention. This is in this paper of Dunkl. Okay, so you can blame him for this strange choice of word. Okay, so we just saw how to get this Vk, which is again the kth eigenspace of the Johnson and Kneser graphs. And we did this by taking this delta operator. So the kernel was Vk. Now, the image is just this smaller slice. And if we now apply delta again and take the kernel, we'll get Vk minus 1. And so on and so forth. So the end result is more generally Vd is the space of all harmonic multilinear polynomials of degree d. Okay, and this is what I think of as an explicit description of all the eigenspaces of the Johnson and Kneser graphs. So as an example, okay, so we won't do V0 because V0 is just all constant functions. But V1 is the collection of all functions of the form sum of Ci xi. So I remind you that xi is just one of the inputs. So it's 1 if I is in the set and 0 otherwise, such that the sum of all the Ci's is 0. Okay, and we can go on and on for the other eigenspaces. Okay, so this is our first step. Now I gave you some sort of an explicit, for some notion of explicit description of the eigenspaces of the Johnson and Kneser graphs, or really of the Johnson association scheme. Okay, so questions about that before we give another way of doing the same thing? Okay, so let me move on. So this was Dunkl, and now we're going to do the same thing more generally using ideas of Stanley. Okay, so Stanley gives us a different way of thinking of these polynomials. So we look at the subset lattice. So here's a part of the subset lattice. So for okay, so there's nothing too exciting here. This is the empty set, and this is the Hasse diagram of a part of the subset lattice. And the idea is that we can think of a polynomial as just giving coefficients for some functions. So this is the coefficient of 1, this is the coefficient of x1, this is the coefficient of x2, x3, and so on. So in other words, another way of representing a polynomial is by giving weights to the elements in the subset lattice. Now we have some target layer. Let's say we're looking at the slice 3, 2. So this doesn't, it's actually not kosher because k is more than n/2, but let's ignore it. So this means that we're looking here. Okay, so how do we interpret this polynomial? So really I just need to tell you how we interpret a monomial. Okay, so let's pick, for example, oops, this guy. So what is the monomial corresponding to this guy? What is the function on this level which corresponds to this guy? This is all the points which lie above it. Yeah, so if we're working here, this is our domain, and we're looking at the function x3. And the function x3 is equal to 1 on all the sets containing 3 and 0 otherwise. Okay, so this is just another way of thinking of polynomials. And the reason we're doing it is because this works more generally. So here, this is the subset lattice, but we could also do the same for the subspace lattice, for example, where these points won't be subsets, it will be some subspaces. Okay. Now, this delta operator that we had above, so let's see its definition again. Yeah. And this operator that you just take the sum of all partial derivatives. So this corresponds to a different kind of operator on the lattice, which has several names. So maybe one of you can say what name they know this operator by. Okay, so if I if I have a polynomial which is represented in this way, I give some coefficient to every point in this subset lattice, and now I apply this delta operator. So what is the effect on the lattice? Have you seen this kind of operator?
Well, it's like when we delete one of the keys at the first level, and then all its neighbors.
Right. So this goes by various names, but we'll call it the down operator. So delta is the same as the down operator. D. Okay. Sometimes it's called the lowering operator. It has an adjoint, which is the operator, the up operator. There is also the up operator U, which sort of just goes the opposite way. Okay. And if you take first D and then U, or first U and then D, then you get something which is known as the Laplacian. And you probably heard about it. Yeah, and in particular, if you do this for this particular lattice, then you get more or less the Johnson graph. Okay, maybe with some kind of laziness. So there will be some self loops that you have to remove. Now, it so happens that du and ud, if you run this on layer L, then the difference is something like n minus 2L, or maybe it's 2L minus n. So hope I'm getting this right. Okay, so these operators, if you do the multiplication in the right direction, then you get this kind of identity. Okay, and this kind of lattices satisfying, or rather posets satisfying this kind of identity were called sequentially differential posets by Stanley. Okay, so you can look at the eigenspaces of the Laplacian. Okay, and it turns out that you can get them in exactly the same way as we had above, by looking at the kernel of the down operator. Okay, so I won't describe it explicitly, but this is another way of looking at the same decomposition into eigenspaces in a more general setting. And this way you can do it, for example, for the Grassmann graph, and it still works. Okay, so these were two ways of looking at the decomposition into eigenspaces. One was using this strange delta operator, which we looked at the decomposition given to us by representation theory, and the other one was lattice theoretic, and you'll have to believe me that using this kind of relation, then you can make everything work. And if not, you can look in this book on what's it called, Spanner theory. So it's all worked out. Okay, so this gives us a description of the eigenspaces, but maybe we want more. Maybe we want to know what do these functions look like? Like, give me a simple example of a function in the dth eigenspace Vd. Okay, so this is our next stop. So this is, I think, 4. So this is in a paper of, I think, Dunkl and Graham. I always forget. So in this paper, they give several proofs of the Erdős-Colorado theorem. It's called all the new proofs of the Erdős-Colorado theorem. And one of the proofs is using the Lovász theta function. And for that, they need to compute the spectrum of the Kneser graph. Okay, and to do this, then they give a basis for each one of these eigenspaces of the Kneser graph. Okay, so let's see how you would do this. So a reminder, Vd is the dth eigenspace of the Kneser graph. Okay, so what is the dimension of VD? So this is really something that we should know because of this delta business. This is n choose d minus n choose d minus 1. Okay, so let's say I'm trying to construct a basis for VD. Then my index set needs to have exactly this size. Okay, so this size, it needs to be counting something. Okay, and it's not so obvious what it's counting. So when I gave a version of this talk in the Hebrew University, then people immediately knew what this thing was counting. Maybe because they teach elementary combinatorics. But I think for the rest of us, it's not so clear unless we already know, I don't know, some representation theory. Yeah, so what is this thing counting? So there are several interpretations. One of them is ballot sequences, but we will use a different interpretation. So this is counting, this is the number of standard Young tableau of shape n minus d. Okay, so what does this mean? So here's the Young tableau. It looks something like this. Okay, so this is n minus d, and this is d. So it's filled with the numbers 1 up to n. It's increasing to the right. And it's increasing down. Okay, so it's increasing as we go in this direction and also in this direction. Okay, so this thing is actually counting the number of Young tableau. And actually, representation theory gives us also a form of a vector in this Specht module that we can describe explicitly. So let's say that the top row is A1 up to AN minus D, and the bottom row is B1 up to BD. Okay, so we get a function we call omega B1 up to BD, which is the following function. XA1 minus XB1, XAD minus XBD. Okay, and this is a function in VD. Okay, so this sort of follows from the construction of Specht modules, but also you can check that if you apply the delta operator on this thing, then you get 0. And really to check it, because all of these coordinates are different, and it's enough to check that if you apply delta on this kind of degree 1 polynomial, then you get 0, which is pretty easy. Okay, so this is a one vector in VD. But if you go over all standard Young tableau, then you get a basis for VD. And what is the reason? So if you look at these polynomials as you vary over all standard Young tableau, and you arrange, like you write them in a matrix of coefficients, so you consider the coefficient matrix, and you arrange the monomials with respect to the right lexicographic order, then this matrix will be triangular. And actually, with respect to the same order, then this will be a Grobner basis. Okay, so these functions are linearly independent. as can be seen via the coefficient matrix. And so basis for VD, since there are exactly dim VD of them. Okay, so this is all in this Funkel-Wilson paper. And now, given this, it's a really easy exercise to calculate the eigenvalues of the Kneser graph, and I encourage you to do this exercise. Yeah, this is really very, very easy. Okay, so you just need to take a particular one of this function, and then there will be well, let's say that you chose a set containing all the a's. Then it's the only neighbor for which this function is non-zero is if you took all the b's, and then you have to choose the remaining points, and you get a sign of -1 to the d because you change sign for each one of these factors. It's very easy. Anyway, I just explained how to do it, but you can do it more slowly at home. Okay, so this is how to get some kind of basis. But we're not happy yet. Okay, so why are we not happy? Because this basis is not orthogonal. Okay, so this is one reason not to be happy. The other reason not to be happy is if I give you a function, let's say it's lying in VD, and I want you to represent it in this basis. Yeah, so I want to compute some sort of Fourier transform. Can you do it efficiently? Yeah, so it's not clear, but it turns out that this orthogonal basis that I'm going to describe also allows calculating these coefficients efficiently. Okay, so this would be part 5. Okay, and this is due to Ambaïnis et al. So these are people doing computer science, or Srinivasan. This is a mathematician from IIT Bombay, and also due to others, such as myself. Okay, but I'll give a construction due to Nathan Lindzey. Okay, so we had these functions. Sorry, I'm having some troubles moving things around. But hopefully this will get fixed in a moment. Yeah, so let's say we want to find an orthogonal basis for BD, and we have a basis for BD. So what is a way to get an orthogonal basis from a basis?
Gram-Schmidt.
Right, Gram-Schmidt. So to get an orthogonal basis for VD, we arrange this other basis in the correct order, in this same lexicographic order, suitably defined, and run Gram-Schmidt. Obtaining a basis, what you call Chibi, and I'm going to describe it soon. Okay, so this is the construction of Nathan Lindzey. And here is a different construction due to Srinivasan. And I think it also appears in this paper from Ambaïnis et al. So we take the empty string to be 1, and then phi of B1 to BD. So this is going to be, we apply the up operator in BD minus 1 to B1 up to BD minus 1, and then we subtract B1 BD minus 1 times xn. So I hope I got it right. So soon I'll give you an explicit expression for the result. But this is the inductive construction due to, let's say, Srinivasan. But I think it also appears in this paper of Ambainis et al. And using these formulas, you can compute this kind of Fourier transform. So express an arbitrary function in VD as a linear combination of these basis vectors very efficiently. Okay, so this is why these things come up in a paper on quantum complexity of all things. Okay, and now we're going to give this explicit description. So this is going to be my work. So this B1 up to BD. We're going to sum over all A1 up to AD such that AI is less than BI, and all the A's and B's are distinct, but we don't require the A's to be increasing, of XA1 minus XB1, XAD minus XBD. Okay, so sort of if you unroll this recursion here, assuming I wrote it correctly, then you will get this explicit form. Yeah, so if you go over all standard Young tableau of shape n minus d, and for which one of them you write these b's, and now you compute this kind of vector, rather you compute this kind of sum, then the resulting collection of functions is an orthogonal basis for VD. And if you do this for all D, then you get an orthogonal basis of eigenvectors for the Johnson and Kneser graphs. So I think this formula is nice. I'm not sure that it has any applications, but it's maybe a bit surprising. Definitely, I wasn't expecting it. Now, why did all of these constructions get the same basis? So one explanation is this basis is actually a canonical basis. So this basis is the Gelfand Tsetlin basis, or GZ basis, which means that it consists of common eigenvectors of the Young, Utsis, Murphy operators, which are the following. Yeah, I is a bad letter, so let's choose something else. Okay, so what does that mean? So if I have a function, then I can apply one of these transpositions on the input. Now I do it for each of these transpositions, and I sum the result. Now I get a new function. So this is how this operator is defined. And this basis here that you see here, it's an eigenvector of all of these operators. And you can describe the eigenvectors explicitly. It's not very complicated, but we won't do it here. So this is some kind of canonical choice of basis, which it's canonical only up to an ordering of the numbers 1 to n, and of course up to a constant multiple. Okay, but this does mean that we sort of found the right basis. Yeah, so questions about this before I summarize and suggest some open questions. Okay, so I'm just looking for the number. So, oops. This will be open questions. So there are other graphs to explore. Okay, and here are two examples. So one example is the Grassmann graph. And the other one is the derangement graph. Okay, so the Grassmann graph is the Q analog of the Johnson graph. So now the vertex set, instead of being subsets of size k, they're going to be subspaces of dimension k over some finite field. And there are subspaces of some universe of dimension n. And you connect two of them if their intersection has dimension k minus 1. So this is the Grassmann graph. And you can also look at the Kneser graph. So now you connect two subspaces if they trivially intersect. And the other graph is the derangement graph, which is the graph from the symmetric group, where you connect two permutations if they disagree on all the images. Okay, so I'm not writing it because these graphs are somewhat familiar. And so for each of these graphs, we know the eigenspaces. In this case, from, let's say, the theory of the Grassmann association scheme. Okay, but you can also construct them from the subspace lattice because this the subspace poset is also sequentially differential. And in the case of the derangement graph, the eigenspaces are just the isotypic components of the symmetry group. Okay, so they're known explicitly, however explicitly we want. So what is not known? So for both of these cases, it's possible to give a description of the eigenspaces as we saw above. So yeah, so here we said that VD, this is the dth eigenspace of, let's say, the Johnson graph, is the space of all harmonic multilinear polynomials of degree D. Now, this description of VD also works for the Grassmann graph, okay? Where now our polynomials, the monomials are in the subspace lattice instead of in the subset lattice, but everything else is the same. So this kind of description is still correct. In the case of the symmetric group, then you can look at a more coarse decomposition, okay, into some kind of spaces VD, where for those of you who know representation theory, D is going to correspond to the number of cells beyond the first row. And then there's also a description of this form that was recently worked out with Nathan Lindzey, where now you have to define harmonic in a perhaps less obvious way. Okay, and from this, in principle, you can get a nice description of the actual eigenspaces, but I don't think we worked it out. Okay, so this is all things which are known. What is not known? So what we don't have is this kind of nice description. Okay, so I think Srinivasan has this kind of description in some sense for the Grassmann graph. But he asked me when I visited him, is there a description of this sort? Okay, so it's not completely clear how to do it. Nathan and I tried for a while and we couldn't do it, but now we seem to be more optimistic about this. So maybe in the future we will do it. In the case of the symmetry group, in principle, this is solved by the Young orthogonal basis, which is also another way of obtaining this basis, but what the actual formula looks like is not so clear. Yeah, so the open questions here are find analogs of the explicit formula. Now you can ask, is this actually good for anything? Is there any reason of doing it? Why am I listening to this talk? Shouldn't I be doing something else? So I must say that I don't have a very good answer for this. I think this kind of formula is very suggestive. It's nice to know that this kind of thing is true. There is some interesting mathematics involved when extending this to other domains, for example, the symmetric group. But whether there are actual convincing applications to other areas beyond just people interested in this sort of thing, and I don't have a very good answer. But this is the way we do mathematics, I think. So we don't always ask the same questions, the right questions, and so we don't always provide the right answers. But if the mathematics is interesting, then you can say that it's not all in vain. Or at least that's what I think. Okay, so that pretty much covers all I had to say. And if you saved all your questions to the end, then now is the end.
Thank you very much. Yeah. Does anybody have any questions?
I have a question and comment.
Yes.
I just wanted to mention that the what you call the sequentially differential poset idea there's a generalization of it called a uniform poset. A uniform poset. I wrote a paper about this back in the early 90s. And the examples you mentioned are all in special cases, and there are many more examples as well. Anyway, I just tossed that out there in case you're unaware of it. There's a very interesting representation theory of the algebra generated by the lowering and raising operators for any uniform poset.
Yeah, so thanks. I wasn't aware of this, and I will definitely look it up. I should say that there is some recent work on high-dimensional expanders, which you can think of some kind of specification of, let's say, the subset lattice, which is not quite, doesn't quite satisfy this, but almost satisfies this. And then you can do all of these things approximately. So on the same topic.
Yep.
Oh, Joshua has a question.
Oh, hi. Sorry if this, can you hear me?
Yes.
Sorry if this is not a smart question, but what's the inner product on the polynomials? Is like are the monomials an orthonormal basis?
Yeah, you just so you think of them as functions on the vertices of the graph, functions on the slice, and then you just you multiply the two functions and you take an expectation. Or if you just care about orthogonality, you can also just take a sum. So I'm presenting them as polynomials, but I'm thinking of them as functions.
Okay. So like the vertices of the graph or their characteristic functions are the orthonormal basis to start with?
Right, right. Exactly.
Okay. Thanks.
Now, so Joy Everson has a question.
Hi, thanks for an interesting talk. This is a little outside my area, but I was just curious, is in some sense what you're doing here finding a change of coordinates from like the spec module to Young's orthogonal form?
Yeah, and actually when I found this explicit form, I just looked at some matrix form of the Young orthogonal basis, and I looked at one of the coefficients. Yeah, so what you said should be true, but I don't completely understand it.
I see. Okay, thank you. I was actually wondering about that the other day. So since I'm talking to you right now, do you happen to know any other kind of references I can look up for that kind of thing?
Well, let's see if Nathan is on.
Yeah, let's see. So Joey, were you looking, so were you starting with like some sort of polytabloid basis, and you were trying to write things in term like I guess what was the domain that you were considering?
I haven't done it yet, but sure, let's say polytabloids.
Okay. So there, so I'm not aware of any. I'm not aware of any papers where these things are worked out explicitly, and this is sort of why, like I think these results are interesting. But maybe, yeah. The short answer is no. I don't know a place to find these types of results for other bases.
Okay.
Yeah.
Cool. That was.
I think sort of what is. I think sort of the point is that algebraists typically don't think in these very concrete terms. For them, it's too concrete, and they prefer the abstract point of view. And this is why they don't care about anything.
I see. But you know, at the end of your talk, you were sort of saying like, why should I care about this? And I think that's a very good answer, right? Those are two fundamental views on the representation theory of the symmetric group. And this is drawing a bridge between them. That's fundamental.
I'm sold. Yeah.